Okay, so since a lot of you said that you're not super familiar with, you're not yet super comfortable with set theory notations and or would like a refresher, um, let me just go through some of the basic definitions and properties of the set theory notation. Okay, so first of all, when we talk about sets, I said that there should be a very precise defining condition to be if it should be able to say whether something whether an element belongs to the set or not. And the reason behind that is otherwise it leads to something called the Russell's paradox. Russell's paradox. Paradox. So what does Russell's paradox say? Let R be a set. Let R be a set of all sets. All sets that do not contain themselves. That do not contain themselves. Then does R contain R, right? And this is called a paradox because if R contains itself, then by the defining property of R, which is the sets should not contain themselves, R should not have contained itself. However, if R does not contain itself, by its defining property, it should have contained itself. So this is an example where R is not really a set, not really a set, even though it is a collection of objects, even though it is a collection of objects. Okay, so this is one example where you can not tell using the property whether some element should be in the set or not. It creates a paradox, and that is what we need, the condition that you should be exactly able to distinguish for. But don't worry, we are not going to be looking at such things again. Okay, all the sets we use will be pretty well defined, and you can tell if certain things should belong to it or not. Okay, given a set, definition, given sets A, B, given sets A, comma B, we define A union B to be equal to X such that X is in A or X is in B. Okay, now the OR does not rule out that it could be in both. This is the mathematical OR, not English OR. English OR says, oh, if X is in A or X is in B, then X cannot be in both. Mathematical OR says, if X is in A or X is in B, it is allowed to be in both. It should be in at least one of the two. We define A union B to be this, and A union intersection. A intersection B to be all X such that X is in A and X is in B. Okay. Further, we define the relative complement, define B minus A, which is equal to relative complement of B in A, of A in B, of A in B to be equal to X in B such that X is not in A. Okay, so this is also sometimes read as B minus A. Okay, set B minus set A. This is the formal definition. This is a symbol for definition, but the others are how you read them as. Okay, if you are given a global set, a universal set, so if there is a universal set X, X, and all other sets and all other sets are understood to be subsets, to be subsets of X, right? Then we can say then the absolute complement generally denoted a complement or a bar is X in X such that X is not in A. Okay, so if there is a global set that we know that we are going to talk about, we don't need to say in this side what set we are talking about. You can say, oh, just A complement, or the complement of A, and it will be assumed that you're working with the largest set that you have, the global set. Okay, so you see there's no X on this side, on the left hand side, and we are just going to assume that it is there. Okay, and note B minus A is actually just B intersection A complement. Okay, so why? Because, well, B is also a subset of X. What is the condition of B minus A? Well, X should not be in A. Well, if it's X is not in A, then it is in A complement, and X should be in B. Well, how do we make sure that happens? Take the intersection of B and A complement. Okay. Properties of union and intersection. Properties of union and intersection. Well, first, it is commutative. So A union B is equal to B union A, and A intersection B is equal to B intersection A. Okay. Second, associativity. OCIAtivity. What is associativity? Well, A union B union C should be equal to A union B union C, and A intersection B intersection C should be equal to A intersection B intersection C. So the order should not matter. Okay, if you're doing the same, And third, distributivity. Now here we have the interaction of union and intersection with each other. A union B intersection C is equal to A intersection C, A intersection C union B intersection C, and A intersection B union C is equal to A union C intersection B union C. Okay, so both of these behave nicely, and in light of commutativity and associativity, we can say A1 union A2 union A3 dot 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 union dot 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 union AN makes sense, because this is just A1 union A2 union dot 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 union AN. Okay, and similarly A1 intersection A2 intersection dot 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 all the way intersection AN is simply A1 intersection A2 intersection dot 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 intersection AN. Okay, so both of these quantities now make sense now that we have defined how union and intersections work with each other. Sorry about that. And the shorthand notation for writing this is going to be A1 union A2 union dot 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 AN is going to be written as union AI, I in I going from 1 to n. I is equal to 1 to n. If they are in some set capital I or something, I will write them as I in I. Or if I'm labeling them as natural numbers, it's an infinite union, it would be I in naturals. Okay. Similarly, A1 intersection A2 intersection AN is going to be written I is equal to 1 to n AN. Okay. If the context is clear, I might drop the I is equal to 1 to n if I'm looking at a very particular intersection or union. Okay. So definition: let A be a collection of subsets of let A be a collection of some subsets of X. Okay. Then the union of all these subsets, then the union of all these subsets is denoted union is denoted union A in A in A of A. Okay, so I'm not going to label these by AI or AN. Oops, that should have been an AI. I'm not going to label these sets. I'm going to say, oh, all of these sets have technically different names. They could be A, B, C, D, whatever the names I'm choosing. But these, I'm moving over all the elements of my big set, funny looking A. Okay, and this union is going to be X and X, such that X is in at least one AI. X in A for at least one A in A. Okay. Similarly, the intersection of all these sets, these subsets is denoted intersection A belongs to A. Just a second. Intersection A belongs to A of A, which is equal to X in X, such that X is in A for every A in A. Sorry. Okay. So for every A in A. Now, these are the definitions and elementary properties of unions and intersections. Now we get to the first important result, theorem, De Morgan's laws. De Morgan's laws. Okay. If A is a collection of sets, well, let's say subsets. Okay, maybe they're subsets of X or whatever, it doesn't matter. And X is another set. Okay, then the following equalities hold. Then the following equalities hold. First, X minus the union of A in A of A. So X minus the complete union is actually the intersection of A in A of X minus A. And second, X minus the intersection of A in A of A is equal to intersection of A in A of X minus A. Sorry, this should have been a union, but this is union of, so yeah, X minus the intersection of all sets A is the union of the X minus A's. So you might have seen this before in terms of A complements, or otherwise just like this. Okay, I'm not going to prove it. If you want to prove it, just look up De Morgan's laws. Proof. Try out as exercise, or look up De Morgan's law. So my recommendation is first try them out as exercise. These are not really hard. Just follow the definition and the rules of distribution. So this is basically actually just the rule of distribution that is a distributive property that is being used along with the proper definitions. Okay, once you do that, things will be perfectly fine. You can use that you can use, when did it go? you should use this definition of complement, b minus a, okay, and that should work out. It's a pretty easy exercise. Okay, great. Then let us look at functions, and let me just give some small idea of relation. Relations. So a relation from a set A to set B, a relation from a set A to set B is a subset of A cross B, which is defined as all pairs A comma B, such that A is in A and B is in B. Okay, so I'm going to be looking at all pairs AB. A relation is a subset of A cross B. Okay, we sometimes write A R B to say A is related to B. To say A related to B. Okay. Definitions. So here are some of the common terms of some sets. Let R be a relation on set A. Let R be a relation on set A, i.e. A cross A. Okay. A relation on set just A means it is a subset of A cross A. Okay. This is not the first property. This is the initial setup. Then the first property is R is reflexive. R is reflexive. Reflexive if A R A for every A in A. Okay. If A is related to itself for every A in A. Second, R is symmetric. Symmetric if A R B implies B R A. Okay. Third, R is anti-symmetric. R is anti-symmetric if A R B implies if A R B and B R A implies A is equal to B. So R is anti-symmetric if whenever you have A related to B and B related to A, they have to be equal. So if there are two different A and B, only one of the two should be true. If either A is related to B or B is related to A. An example of this, if you want to think, is the relation that A is greater than B. Greater than or equal to B, if you want. So the only time that is possible is if A is greater than or equal to B and B is greater than or equal to A, then A has to be equal to B. Okay? R is transitive if A are B and B are C implies A are C. If A is greater than or equal to B, B is greater than or equal to C, then A is greater than or equal to C, right? This is a example of a relation. Some other examples include A is related to B if A and B, if A divides B, okay? Or if they have a common GCD. All of these are relations. If they have a common GCD, this relation is again symmetric, or common GCD more than one. It is reflexive. A and A always have a GCD. It is symmetric if A is related to B, they have a GCD, then B has greater GCD than A. However, it is not transitive. 6 and 2 have GCD 2, 6 and 3 6 and 3 have GCD 3, but 2 and 3 have GCD 1. So this is an example of something that is reflexive and symmetric but not transitive. There are many types of relations. Not all of them have to satisfy all of these conditions. Okay, but definition, since we'll be using this soon, I am going to define it right now. Definition: a partial order is a relation. A partial order is a relation on A that satisfies a partial order which is generally denoted. Let me just erase this part. A partial order, so generally denoted something like this. It's more or less less than or equal to, but with arched smaller than sign on a set A. On a set A is a relation on A satisfying the following properties. First, reflexive. A is smaller is A is smaller than or equal to A for every A in A. Second, anti-symmetric. A smaller than or equal to B and B smaller than or equal to A implies A is equal to B. And 3, transitive. A smaller than or equal to B and B smaller than or equal to C implies A smaller than or equal to C. And the question is, why is this a partial order and not just an order? What is the defining thing that makes it a difference? And that is the following property. A total order strictly smaller than or equal to on a set A with partial order this has the additional property that all elements should be comparable. Comparability. does that mean? If I find a comma b in A, then at least one of the following should hold. Then at least one of the following should hold. And what is the one of the following? Well, at least one of, I don't even want to say following. One of A smaller than or equal to B, or B smaller than or equal to A should hold. Okay. My total order and my partial order look similar. So this should be proper straight lines, which I am not very good at drawing, and these are curvy lines. These are not straight. So, whatever, you get the point. So this should hold for every A or A and B. Then this is a total order. Okay, and we can write this is actually equal to A smaller than or equal to B, or B smaller than or equal to A, right? Because the partial order and total order are going to be the same thing. Okay, there are quite a few things like this. Another important condition is definition, an equivalence relation, definition, a relation, an equivalence relation, tilde on a set is a relation. Set A is a relation that is reflexive, symmetric, and that satisfies the following properties. Properties. First, so partial order was reflexive. This is also reflexive. Just to say A tilde A for every A in A. Symmetric. A tilde B implies B tilde A. And transitive. So unlike partial order, this one needs symmetric instead of anti-symmetric. Okay. If A tilde B and B tilde C, then A tilde C. Okay. So let me stop this one here. I will discuss some properties of functions in the next part of this video before we get into higher details. Today's lectures is going to be just on these topics, since this is a lot.